So
Cool.
the stage is yours.
Thank you. Yeah, hi everyone. I'm Diganta. I'm a research master's at Mila in Montreal. Currently, I'm at Carnegie Mellon. Um, yeah, as was mentioned before, I'm also the founder of Landscape. It's a very small research nonprofit org, very similar to Eleuther. We started out in 2019, and we just wanted like we are just a bunch of people from different background, like film producing, physics, mathematics. We just wanted to like gel together and work on some ideas collaboratively. So yeah, Landscape was formed with the spirit of providing a foundation for a multidisciplinary collaboration and ideas pertaining to AI. So that is pretty much what I've been up to. And today in this talk, I'll be uh, going over this new paradigm of deep learning, which is to utilize synthetic data for training and more focused on lifelong learning perspective, which sort of combines well with the theme of this reading group on EfficientML. So the first part of the talk will be about a bunch of papers, literature, and this general paradigm of what synthetic data is, how we can use it, and then we'll go into the specifics about my work, which we released a month ago. So yeah, feel free to interrupt me if there's any questions in between. Um, okay, we'll start with a quick eye test. I've sort of used this format in my other talks as well. I usually like them interactive, so if the chat is enabled, feel free to write your answers in the chat. I'd be very curious to see what people's perception are. So we have like three candidates here, Charlie, Foxtrot, and Daisy. You can write in your chat which one you feel is a fake image or a generated image, and which of these dogs are real. So I'd be curious to see what people have to say on this. Just quickly open the chat if people are writing here. And yeah, let's see how many people can get fooled. I don't see any messages yet. Daisy and Charlie. I guess Daisy is real. Charlie is fake. Okay, so when people are writing just the name, I presume people are writing the fake dog's name or the real dog's name. If you could just write only the real dog's name or the fake dog, whichever is fine. Charlie and Daisy are fake. Okay, okay, nice. Well, Daisy is fake, real is Foxtrot. Okay, okay, I see. Okay, so cool. Yeah, there is no general consensus. It seems people are gravitating towards mostly Charlie being fake, which is correct. Charlie is a generated image. But if you guess Daisy is a real image, then you're incorrect. Daisy is also a generated image. The only real candidate here is Foxtrot. So quite perceptually remarkable at this point that it's so hard to differentiate between real images and synthesized images, given how powerful image generators have become, especially these images that I've generated with Charlie and Daisy. They're not like very powerful models or state-of-the-art models. They are both generated from Stable Diffusion XL Lightning, comparatively a smaller and somewhat good model, but I wouldn't call it a state of the art. So you could assume that if I used an improved model, maybe I could have fooled all of you. But the point I'm trying to make over here is that like we have definitely seen these models become more and more capable towards generating photorealistic images or concepts that become perceptually indistinguishable from actual natural world. And I got this quote from ChatGPT, and yes, I got it from ChatGPT after a couple of prompting tries, which is what essentially is generated data. And we know, like, we live in a world where scaling is such an important proponent of deep learning, especially we want to squeeze the maximum performance out of the models that we have, the compute that we have. People have been heavily reliant on scaling data, scaling models, but also it becomes important to recognize the importance of data beyond just the model architecture design and the optimization paradigm that you're using. And you might have heard of these general statements that data is the new oil, representing like the new economy essentially, and those that have more data basically are those that strive in this field. And I definitely agree with this quote that data is wealth, and generative data is sort of one step above just the raw data that we can get from the natural world. Uh, and this has been sort of very evident with the way we have gone from this earlier papers where we used to have these granular face images being generated. If you have read the Eigenfaces paper or something around those time from DC-GAN, you might have seen all these papers trying so hard to get a pixelated black and white image of a face. Doesn't look anything like a photorealistic image. You might think it comes like, even if it is photorealistic, it looks like it's taken from a camera from 1900s or something. But now the facial images are so vividly striking and photorealistic. You can see the individual wrinkle lines. You can see perfect strands of hair and every other facial attribute that a photorealistic or an actual person's image would resemble. So definitely a quite a impressive progression from where we were maybe just a decade ago. I completely understand that in deep learning field, a decade becomes historic at this point. Like a paper from 2015 might be called like history at this point, but it is the fast rate of progression in our field that we are currently in. So the point being that we have come far from just generating images of faces of humans and just of cute dogs, but also to faces of varied styles, right? Can now generate not only photorealistic images of humans in different poses, different lighting conditions, but we can also compose images of different scenes and different styles, like artistic paintings and renderings of cities or ports or harbors in with different color palette. But we can also generate compositional concepts that you just wouldn't see in the natural world, right? Like you wouldn't see a fox eating bunch of popcorn in a cinema, but we can generate it using these image generators because they have learned to model the representations of different concepts that do occur in the natural world, but just not in composition of each other. So now they have the capacity to compose them together to create one single coherent scene, which is honestly very impressive. And this has led to the point that now I don't have to convince you that this is economically very appealing. It is also economically very appealing to pretty big corporations, right? So you have Google, OpenAI, Stability, Pika, Meta, and so many others like major players in the field who have been putting a lot of effort, money, resources into utilizing synthetic data and also building superior synthetic data generators, right? So I believe at some point, each one of us in this call has played around with some kind of image generator and created a new image and have been really astounded by the quality of it. So that's all coming to the part that these companies are putting that much effort into creating these state-of-the-art models. So I want to shift the narrative from this paradigm of supervised training that arguably has been the gold standard for many years in probably all fields of deep learning to this new paradigm of generative supervised training. And this is nothing, I would say, groundbreaking because there are papers that sort of have encapsulated this idea in some form or the other. Starting out with a few papers that I want to highlight is like one paper from Google. They recently explored this idea is how we can augment our real data set with generated images and train a new model on the union corpus of real plus generated data, and they did it at ImageNet scale. ImageNet maybe is no longer the most difficult task these days in image domain, but it's still quite impressive to see that when you go from just the real domain to real plus generated, you can expect to get a considerable amount of improvement depending on what you call statistically significant. I do presume that these improvements are non-trivial, and not just in domain performance but also in out of distribution performance, which is great because we want our models to be robust. And similarly, there are works where people have tried the best way to generate it, these synthetic data to augment your set. And this all comes to the underlying principle of data augmentation, right? We have all read about data augmentation, the benefits of augmenting your data with different styles, different spatial composition, or just mixing up images using mix-up or cutting out some patches. So all of these have come to the point that we want our data to not be a narrow, limited view of the world that we want a model to learn the representation of. So ideally, we want to diversify it, right? That's the whole goal of it. And this is not only confined to image classification, especially single object image classification setting, but it has been done in multitask setting where you want to generate task specific data. And it has been done going beyond images in image language settings. So now there is a paper called SynthClip where they can train a clip fully end to end. So if you're not familiar with CLIP, it's the contrastive language image pre-training model by OpenAI, where you have a language encoder, image encoder, you have a contrastive objective to minimize between the two. And they have trained these models end to end with only synthetic data. So synthetic captions, synthetic images, right? So quite impressive to the point that now we are capable of training multimodal models purely end to end from generated data. And if all of you are not from the background of images and maybe images is not very appealing to you, then do not worry. It's not only confined to images. There are works which already do synthetic data-based training approaches on audio. I'm not an audio guy, so I don't know much about the space, to be honest, but I found this paper from 2021 where they have used synthetic audio in training for keyword spotting. And of course, it makes sense for embodied agents to also be trained on some form of synthetic data where you can simulate an environment using synthesizing that environment in some specific software. If you can create an environment in Blender or any other software which you can simulate using an RL agent, that's also very useful. So all of these boil down to the same narrative that utilizing synthetic data for training is definitely useful than simply relying on natural available data. But recall that I started out this talk with the motivation that current deep learning scale relies a lot on scaling. We want our models to scale, we want our data to also have a positive scaling effect, and we want the scaling to give us positive reward, which means that we want performance improvement that we can essentially model into a power law, and we can predict how much we can get by increasing the data scale or the model scale, right? So natural question becomes is, can we scale the generated data and in such a way that we get positive reward out of it? There is a paper that tries to answer this. However, the answer is a bit complicated. So I would not call this answer to be conclusive. But what they do is they scale ImageNet to different volumes. Like volume, I mean the number of samples. And they see some improvement in out of distribution, zero shot accuracy, in distribution performance, and they try a bunch of different settings. It does show scaling helps, but their answer is not that it helps always. Like there's some bottlenecks to it, and it's not like it's not a one-stop solution that you can just train on generated data and get always a better performance than the available natural data that you have. But I question these conclusive findings to be inconclusive because of various assumptions, right? Like we all know if we have played with image generative models that they are not particularly stable, right? Like you can have very distinct images based on prompts for the same concept. Like for example, draw an image of a photorealistic poodle on a bed. Just change two or three words in this prompt, give it to the same model, different seed, and voila, you'll have a very distinctively different model, right? A distinctively different image, I'm sorry. And not only that, they're sensitive to the prompts, but they're sensitive to hyperparameters. Like if you are familiar with stable diffusion, there are a lot of hyperparameters, right? There's guidance scale, there's the configuration you're using, number of sampling steps. All of this comes into play when you're generating these samples, especially when you're generating to train on it. And more importantly, you have to also take into account that we have so many image generators out there. Stable diffusion is definitely a very strong model, but it's not the only model. And most of the papers that I showed you before, they have one shortcoming in my point of view, which is that they rely on one model and one model alone for the whole generation process. This is an important point because this is one thing that we highlight in our work, which I'll show you later. So I wouldn't call the paper's finding to be super conclusive. It definitely does provide really good insights into the limits that we currently have in terms of utilizing generative data for training, but also take into account the assumptions and also take into account that this was only done in a single modality in ImageNet and image classification. As I showed you before that generated data has way more use cases for training than just image classification settings. Okay, so with that, I'd like to sort of go into the specifics of my work, and the work is titled "Just Say the Name: Online Continual Learning with Category Names Only via Data Generation." Uh, Before I even dive into it, the title alone probably gives the scare because it has so many jargons, like there's online continual learning, category names, data generation. If you're not familiar with some of these terms, don't worry, I'll dissect them. Um, the work is in close collaboration with a few of my collaborators from Yonsei University and Seoul National University. So the preprint is out if you want to give it a check after the talk. But let's start with the background of what motivated us to even look at this. So I sort of have given a hopefully a convincing overview of utilizing generated data and the impact of utilizing generated data for training. But what are the other options that you have for training models these days? You, of course, have your manually annotated data sets, which are nothing but the data sets that we have been training on. So if you have taken ML 101, you might have used the iris data set. It is annotated. By annotated, I mean either it has dense annotation, so it has like fine-grained annotations, like semantic segmentation maps or instance segmentation maps, or it is annotated at a more higher cost level. So it has labels, for instance, if you have an image of a dog and you have its corresponding label of the breed of the dog. So that is what manual annotation means. And when I say manual, it means that these annotations have been done by humans primarily. So if you have read some works on pure dataset generations, like the visual question answering dataset, that was curated by utilizing humans and their efforts from the Amazon Mechanical Turk platform, and essentially paying them a lump sum to generate the required questions and the annotations being the answers to each of the visual scenes in the dataset, right? So these data sets are fantastic. They are a really good playground to try train these models on these different tasks and see how much we can get out of it, but they come with a lot of downfalls. One is they are not controllable. And when I say controllable, I mean you only have the images that you have annotated in the data set. You cannot just have arbitrary images of different concepts combined together or compositions of different concepts in different scenes. So you only have a fixed, limited diversity of images. So I'm only specifically talking about a data set of images here. So the diversity is definitely low, and maybe the sample volume is also finite. You do have storage issues. So if you're training on ImageNet, you have to locally store ImageNet somewhere. Sure, storage is very cheap these days, but it's still a non-trivial cost. Most of these data sets don't have any usage restrictions and privacy issues because you assume that all usage restrictions have been taken into account during the curation of the dataset and no private data were incorporated in the dataset in an ideal Oracle setting. But the acquisition cost is quite high, right? Like if you want to curate a really good quality, fine-grained annotated dataset, you have to label using human workers, and yeah, that's going to cost dollars, and it's not cheap. Um, and then we look at the other end of the spectrum. If we want like cheap, humongous amount of data, which is what most of the current foundation models have been trained on, is the option of web scraping, right? So you web scrape like from the internet, from different internet platforms like Google, Bing, Flickr, and you can thousands, if not millions, of images for a specific concept. But you still have some controllability issues, right? You cannot arbitrarily have any image that you want with any composition or any scene. Like you only have access to what people have uploaded or what is available on the internet. But you don't have any storage issue, right? You can do it on the fly. You can scrape on the fly. If you have API access to a certain web search engine provider, you can just keep scraping on the fly and keep training, right? So you don't have to locally store it. The data storage is taken into consideration by the web search engine or the service provider. But you do have usage restriction and privacy issues, right? You must have seen the images with watermarks on it when you search on Google and you see the images. Or they might have written a license protection, so you can't arbitrarily use it for any use case. Sometimes these licenses are also protecting the image from being used for deep learning model training. And there are privacy issues because there are a lot of private data on the internet, like social media platforms. People upload their private images or other form of private data, which you ideally should not and cannot use for model training. But correspondingly, in comparison to manual annotation, the acquisition cost is very low because you don't have to annotate. You just prompt the search engine with the specific concept that you want images for, and you scrape them on the fly. But at the compromise, you also acquire a lot of noisy data, which I will highlight in the next slide what noisy data in this case means. But before I highlight that, I want to present generated data as sort of a cheap leeway to address all of these issues, right? So generated data, fantastic controllability because you can prompt whatever scene you want, whatever composition you want, with whatever concepts you want, and ideally you will get a good image out of it. You don't have any storage issues, just like web scraping. You have to only store the model if you're locally storing it, and you just have to prompt it whenever you want to generate images and use it, but you don't have to store images. In an ideal setting, you don't have any usage restriction or privacy issues. Yes, there are papers that address that deficient models memorize the training set and you can retrieve memorized samples from it, which I completely agree with. But in an ideal Oracle setting, generated data do not have usage restrictions associated with it in terms of utilizing it for model training and don't have private data incorporated in it. And the acquisition cost is very low, right? Like you can use Stable Diffusion for free, so you don't have any cost whatsoever. And the noise is also low, but it's conditional on the prompt and the settings that you're using it for. So what does noisy data mean, right? You can go to the web and just simply prompt images for specific classes from the PSCS dataset, and classes like guitar, dog, house, horse. You'll get images which are good for sure, but you will also get images which just do not perceptually correspond to the specific concept that you want to generate. For example, you'll get images of horse which has an engine as shown here, and the reason for that being is engines capacity in automobiles is represented by the metric horsepower. So the term horse appears on it. And you can have similar noisy perceptual or semantic noise incorporated in web images of different concepts. Like you write house and then you have this placard saying open house. So not what you would want, but you can argue that we can filter it. We can filter all these noisy samples. But again, my counter argument to that would be is that it's gonna rack up cost, right? You need to have some really good semantic parser that can filter such noisy images. And when you keep, adding these filtering mechanisms, not only you're racking up cost, but you're also, decreasing the effective sample volume that you can get out of web scraping. And also to the point that in web scraping, you cannot assume that you have a uniform distribution over each concept, which means that for some concepts, the number of images available, even post filtering, will be significantly lower than for some other concepts, which is no longer a problem in generated data because you can sample uniformly. So that was my first part, which was to motivate the use case of generated data. But then, the other part was the online continual learning, and what is that? So these days we train foundation models on millions and billions of dollars and utilizing humongous computational resources. And uh, people are really astounded by the capabilities as when benchmarked on very hard benchmarking data sets. But the problem is that when you train in traditional ML setting, where you train it once, or what I call as static training, and you deploy it once, it's useful, but you decrease the shelf life of the model quite drastically, because we live in a very dynamic world in the real world where events keep happening, facts get updated, you have more and more data available over time. So to take into account all of this, ideally a model should be in a lifelong learning state, or to increase its shelf life, at least should be kept continually updated, so that it can model as the real world dynamics keep drifting from the point that it originated. Uh, to motivate this, a very simple example is like if you are using VS Code as your preferred editor, then you might have used GitHub Copilot, or you do use GitHub Copilot quite frequently. Really useful tool, but if you prompt GitHub Copilot very specific, right, which is like, give me this piece of code to solve this specific problem or write this function, but you say explicitly that write it in PyTorch 2.3 or whatever latest version is, it ideally cannot do it, because if it is static train, it has never seen PyTorch 2.3. It doesn't know what has changed from PyTorch 2.2 to 2.3. Hence, it cannot provide you reliable code on the new version that you want, essentially restricting the usability of the model. So we want the models to go from the static training paradigm to the continual or lifelong learning paradigm. I'm going to use lifelong and continual sort of interchangeably. Yes, there are papers that sort of conceptually differentiate them, but for me, like the whole paradigm being that we want to move away from one-time training and deploying once to more like continually updating the model and continually deploying it. So our paper is based on the inspiration of this paper that came last year from Oxford, KAUST, and Meta, called From Categories to Classifier, Name-Only Continual Learning by Exploring the Web. Basically, what this paper proposes is this general end-to-end framework for continual learning, which they call continual name-only classification, in which instead of you receiving the data over time, you only receive categories over time or names over time. What that means is these names can be just the label names. So like if you have CIFAR 10, you have 10 classes, like you receive one class at a time or the name of that class at a time. What they do is as they receive the name of the class, they prompt or they query four different web search engines, Google, Bing, DuckDuckGo, and Flickr, and obtain images from these four web search engines, filter them out, and that constitutes the training data set. And then all they do is they train a linear probe on top of a frozen image extractor, feature extractor, or a backbone. So this is the framework. So at task t minus one, they get cats and dogs, and they obtain the images corresponding to those classes, train the linear probe, and then at task t, now they get two extra classes, bears and ducks, and they again do the same web scraping process, train a linear probe. So two issues that I feel for this paper is that one, it's not truly continual because you are doing is linear probing with different dimensions at every task. So there is no update to the backbone, which effectively by default mitigates catastrophic forgetting. So if you're not familiar with continual learning literature, the main goal or one of the key goals is to prevent catastrophic forgetting, where you want the model to continually update and see new data, see new concepts, but you also want the model to preserve its knowledge of the past data and the past concepts that it has been trained on. By effectively freezing the backbone and only training a new linear probe at every task, you don't ideally expect that the model will have any notion of catastrophic forgetting. And the other issue is the issues pertaining to web scraping, which I think I have done enough justice to highlight why it is not the most ideal form of data collection. But remember, at the start of my talk, I said that all of these papers that use synthetic data for training, they have used only one single generator, which is, in my opinion, one of the key drawbacks of these papers, right? I think all of us have used or read about ensemble learning or utilizing multiple models and then merging them. But the general notion of having multiple models that do the same task and then you merge them either in the label space or in the weight space is definitely beneficial, right? So why not have the same exact view for generation? So what we argue is that if you give the exact same prompt and the exact same concept, the concept here is person written within the bracket in the prompt, to different generators like DALI2, DeepFlood-IF, STXL, and CogQ2, they're going to generate very perceptually different images which have different semantics. So for example, look at the first prompt, which is a black and white image of person highlighting dramatic contrast, and look at DeepFlood-IF and STXL. DeepFlood-IF gives images which does adhere to the prompt, but they are all portrait images. So they are very centered around the face of the person, and usually has one specific scene. So it's usually straight looking, not expressive, and just a portrait image. But then look at SDXL. That also is adhering to the prompt, but quite diverse in the semantics of the image that it is offering to us. So you now have a lady standing sideways in front of what appears to be a large window, but it still adheres to the prompt, but is significantly different than what the Floyd IF provides you for the same exact prompt. So these models have been trained on different data, different training paradigm, different compute. So they obviously have learned these concepts quite differently, and they model the representation for these concepts also very differently, right? So the ideal goal should be to utilize the strengths of these different generators in a more ensemble setting rather than relying on one specific model. Because when you rely on one specific model, you're only narrowing the scope of the generation or the representation of these concepts to what that model has learned, which is not necessarily always universal. So given this, we want to first provide the framework that we designed for this paper called as Generative Name Only Continual Learning, or abbreviated as G-NoCL. And this framework is quite simple and intuitive. So it follows that Oxford papers framework, but instead of utilizing web scraping, now we are utilizing generators, but with a few caveats. So again, you have different tasks and you get, instead of just labels, you get categories. And categories can be anything in this case. It can be simply the name of the label, or it can be something more fine-grained like metadata or something describing a particular concept. It's completely up to you. In this case, we only explored the setting of categories being as labels. So you have like dog, cat in task T, deer, bird in task T plus one. What we do is once we obtain the labels or the categories, we pass it through Psi, which is this module over here. And this is nothing but a prompt refinement module. Remember that prompts for text to image conditional generative models serve as one of the, if not the most important aspect of generating good and diverse images. And our goal is to generate diverse images. So we cannot rely on one single prompt to generate our full data budget corpus for those concepts. So what we do in Psi is once we receive the concept like cat, we wrap it in a base prompt, and this base prompt is nothing but the clip base prompt, which is this is an image of the concept name, so dog. And then we iteratively prompt Gemini to provide us a list of meta prompts in diverse scenes and settings and color palettes. And then we rewrite each of those meta prompts in different ways to construct a list of 50 rewritten prompts that we are going to use to sample from the generator. Right, so effectively what we get out of this prompt refinement module is a list of 50 prompts that then we use to query a set of generators, which is DALI 2, STXL, Cognitive, and Deep Floyd, from which we generate n images depending on what our data budget is. But now we cannot utilize arbitrarily all the images that we generate from these different generators. We should have some filtering process depending on what our data budget is or constraint is. So you might argue, okay, let's just subsample from them uniformly, but we argue that is not the best way. So what we instead propose is this delta module, which is sample complexity guidance that is used to filter from each of the generators for each concept. So it sort of effectively provides us a measure of the contribution of each generator into our ensemble, data ensemble. And then we formulate our training data set. And unlike training only the linear probe, we train the full model end to end. Obviously, as you can see, at this point, there is no continual learning method incorporated to avoid catastrophic forgetting. So we couple this framework with continual learning methods like dark experience replay or experience replay or LiDAR. So the state-of-the-art continual learning methods out there, and we benchmark on different data sets, which I'll get to in a bit. What I want to ensure that this framework is rather a blueprint. It's not a fully conclusive framework. So we want to make sure that people who read these papers, who read this paper, the key takeaway is that this framework has interchangeable components. So for example, if you want to innovate a better prompt refinement module, then you can simply swap out Psi with whatever your new prompt generation processes and just simply plug that in here. If you want to rely on some different generators, you can remove STXL, you can plug in some other model. And if you are not satisfied with the filtering process represented by delta, you can also replace that. So this effectively serves as a blueprint of how you can utilize generated data in continual learning, but the components itself are not hardwired. So you have the ability to remove and substitute something else. So what is this prompt refinement module? As I said, the prompt refinement module is nothing but taking the base prompt then rewriting it into meta prompts, list of 10, and then again prompting Gemini to rewrite each of the meta prompts 5 different ways. So we end up with 50 rewritten prompts. Now, to be honest, we did Gemini, right, which is not the most fan favorite model. So people might argue GPT is a better model. And definitely it is possible that or plausible that GPT-4 is a superior model, but we didn't test GPT-4. We instead tested GPT 3.5. And in our case, what we did is we evaluated the rewritten prompts by computing the sentence embedding of it and then simply calculating the cosine similarity, the average cosine similarity between each pair of the generated rewritten prompt, and Gemini had consistently lower average cosine similarity, which basically means that it is generating more diverse prompts, which is what we want. So we do not say it conclusively that GPT-4 won't be better. If you try maybe GPT-4, it can possibly outperform Gemini, but we didn't try GPT-4. Okay, so why don't we rely only on the meta prompts, and why do we have this two-stage process? So when we go from base prompt, which is this is an image of concept, to meta prompt, a couple of them are given here as examples. Like for example, a photo of the concept being person in earth tones. These are all images generated through Stable Diffusion XL, which is one of the generators we have. They give images abiding to the concept, but when we rewrite this meta prompt into its 3 different rewritten versions, there are 5 different rewritten versions, but I just show you 3 over here. You can now see for the same 3 rewritten prompts through Stable Diffusion XL, you'll get way more diverse images. So because our goal is to create as diverse image corpus as possible, we rely on this two-stage process, one where we write the meta prompts and then one where we in a more detailed way rewrite these meta prompts such that we can obtain more diverse images from the generator rather than only relying on the meta prompts. Okay, so now I'll finally talk about the sample complexity as a measure for filtering. So recall, like you can take arbitrary n number of images from each generator, but I said that that is not the best way. So what we do is we rely on this metric called RMD, which stands for relative Mahalanobis distance. If you're coming from out of distribution detection research area, then you might have heard of Mahalanobis distance quite often. So this is not our contribution. This is from a paper from NeurIPS last year where they formulated this relative Mahalanobis distance as a metric to measure sample complexity. So higher the relative Mahalanobis distance means that the sample is harder or more complex, and lower it is, the easier it is. So it can go into negatives as well. So if you see for the same concept with the same prompt from the same model, which is Stable Diffusion XL, low RMD examples are distinctively different from high RMD examples. Like look at guitar, for instance. This is a low RMD example of generated image of guitar. You have the guitar at the center of the image. There's hardly any artifact, any occlusion, any noise. The color palette is quite uniform and distinct from the foreground to the background and the subject. But when you look at the high RMD example, you can now see that the image is of a different view perspective of the same object. It has different geometry, it has different color scheme and palette, and has different artifacts. So definitely not as trivial as the low RMD example. And that pretty much is the story for other concepts as well. When you see a giraffe here, it is very uniform color palette, center of the image, whole body of the giraffe. Now look at the high RMD example. You have way more interference from the background, way more diverse color profile. So definitely the high RMD examples encapsulate the same concepts, but with different levels of hardness. But not only in the case of concepts, it is also in the case of different generators. So remember I told you that we should utilize different generators in an ensemble way because they have different strengths. And that is particularly noticeable in this right-hand plot. So if you prompt different concepts from different generators using the same prompt template, for the instance of the concept candle, Deep Floyd IF on average generates samples with higher complexity as denoted by the RMD score. But when you switch the concept to eyeglasses, then SDXL has way higher average RMD score, similarly for tree. So they're not always uniform. And we have this notion in deep learning that we look at the average metric, which is the average accuracy over the test set. Now, the average accuracy is good, but that doesn't mean that it is also best over each class or each concept, which is also evident in generative models. So some generators are better or can reliably generate more complex samples for certain concepts as compared to some other generators. And this is not only the case with different generators, but also with different prompts. So if you have different prompts with the same model, you're also going to result in generating images which are of different complexity. So for instance, a realistic image of concept provides the average RMD score of 1.2, but a black and white image of concept highlighting dramatic contrast has a way lower RMD score. So some of these are intuitive of why they will have more higher RMD, but yeah, the point being that even prompts can dictate the complexity of the samples that you are generating. And this is just a visual example of some of the low RMD meta prompts and high RMD meta prompts. So you can see for the meta prompts that on average generate high RMD examples, like a photo of a house in neutral tones, has way more detail, way more occlusion, more background interference than the corresponding low RMD image. So based on this, we create a new data sampling process called as DISCOBER. And first, before I go into DISCOBER, I want to highlight what even RMD score is. So RMD score of a sample is nothing but the difference between the distance of the sample from its class prototype and the distance of that sample from the global prototype. So basically, these prototypes are computed by pre-trained feature extractor, in our case, from a feature extractor of a clip model, so visual feature extractor of clip. And then we simply compute the Mahalanobis distance between that particular sample and its class centroid and subtract it from the distance to the global centroid. So effectively, the key takeaway is high RMD refers to as harder examples. So based on this, we compute this probabilistic measure called as DISCOBER, which basically for each concept that we have, that we get over time, we give higher probability of including samples from a generator which generates samples of higher complexity. So effectively, high RMD examples will be given more preference, and low RMD examples will be given less preference for each concept from each generator. But remember that this is a probabilistic measure, so it does have a non-zero probability of the low RMD examples being incorporated. So it's not only that we only take the high RMD examples, but we do also take the low RMD examples. Now, how does this actually work in practice? So you have a few baselines that we can compare with. In this case, we use the PSES dataset using the dark experience replay continual learning method. And we have first a few baselines to go through. So we have the baseline, which is no ensembling, which means that we only generate all of our images using all the meta prompts and the prompt readers we have only from Stable Diffusion XL. So all of our images are coming from Stable Diffusion XL, hence we don't have to do any data filtering because we just take all the images that Stable Diffusion XL provides. Then we have equal weight ensemble. Now we have 4x the number of images because we have 4 image generators, and we have to decrease that to 1x. So we basically do equal weightage to each of the generator ensemBlER. Then we have k highest RMD. So instead of a probabilistic measure, we simply do the top k RMD examples for each concept from each generator and utilize that. K lowest is literally the opposite of that. So we only take the k lowest RMD examples. And inverse probability is basically the inverse of DISCOBER. So high probability is given to low RMD examples and low probability is given to high RMD examples. And then we have DISCOBER. So as you can see, our method is more efficient in the ensembling process than all of these baselines in both ID and OOD settings. Because it's an online continual learning process, our two metrics are area under the accuracy curve and the area and the accuracy at the last point of training. So we definitely have improvements over all of these baselines. So I hope I have convinced you in the usability of this metric. But if you're still not convinced on how the interpretation of this works, then I'll just provide a simple SVM perspective of it. So basically, if you look at the data manifold, then you can visualize these two classes. So you have the classes of samples represented in orange circles and then purple polygons, and the class centroid being represented as the dark patches of those respective shapes. So if you only took low RMD examples, then they will be concentrated around your class centroid. Hence, when you learn a classifier to create a linearly separable boundary between the two, then the degrees of freedom this classifier has to construct this decision boundary is quite high, because you can like if by the looks of it, you can simply draw n number of lines that perfectly separate this cluster and this cluster, right? So the non-highlighted points over here are not being utilized for training. But consequently, if you took high RMD examples, then these high RMD examples mean that they are farther away from the class centroid, but closer to samples of other class. So effectively, you have now a much tighter margin to construct this decision boundary, which fits the data distribution more better than the case of k-lowest. So think of it, the high RMD examples, to be nothing but support vectors. If you're familiar with hard margin support vectors, then these are basically support vectors for your decision boundary to be constructed by the classifier. Okay, so I hope I've given a fair overview of what DISCOBER is and how you can interpret it, but does it actually work in practice? We can see that through our results. So we basically try a few settings, which 4 different data sets: PAX, domain net, CFAT, NW, and CCT, for which we have one ID domain or multiple ID domains and a few other OD domains. For each of them, we have listed a total number of tasks, classes, and the splits of classes per task. This is quite a huge table, so let me try to distill it for you. So this is the primary table of results where we show few baselines. So we have the web scraping, which is the method from Oxford paper. We utilize the same. So all the training data methods you see over here have the exact same data budget. So the number of samples are the exact same. The method column here corresponds to different continual learning methods like experience replay, dark experience replay, plus. These are just methods to prevent catastrophic forgetting. Now you have web scraping, you have base prompt. So that is the original base prompt, and you utilize only stable diffusion XL to generate all your images only from the base prompt. Then you have diversified prompt, which is the prompt rewrites. So you generate images, but still only from stable diffusion XL, but utilizing now the set of diverse prompts. And then finally, you have generative ensemble, which is our DISCOBER method. So now you have 4 different generators, diversified prompt, and then utilize DISCOBER to subsample from it. And then, of course, you have the manually annotated data set for each of them. So you can clearly see that we outperform the web scraping baseline, both in ID and OD setting. In fact, in OD, we also outperform manually annotated set. You wouldn't see that we outperform manually annotated data set in the ID setting, but that is expected because the test sets of these data sets have been constructed in such a way that it favors the manually annotated data set. Okay, is there a question? Yeah, okay, I'm finishing. I have one more slide. Okay, so this is with ResNet 18. The same trend holds in VIT as well. And the absolute last slide is we have a scaling plot where we show that if you keep on increasing the data ensemble size, then both the OD and the ID performance also keeps increasing, and you can fit a nice power law to this. Yeah, that is it. So thank you so much. I am sorry I took a bit more time than I was expecting, but if there's any questions, I'm happy to take them right now.
Great. Thank you so much for your talk. It's an interesting work. Let me stop the recording first before I forget.